In this lecture we are going to see some of the methods by which we can improve the performance of Rankine cycle. Okay, and we are going to solve some numericals so that Rankine cycle is understandable. Okay, now we are going to start methods to improve the performance of a Rankine cycle. Okay, the first method is by increasing the boiler pressure. Okay, now 2 to 3 is the activity of the boiler. Okay, because in this process your heat addition takes place. Okay, in this process your heat addition takes place. So 2 to 3 is our boiler. Okay, now we are suggested to increase the boiler pressure. Okay, so now if we increase the boiler pressure, what it is going to be? If you slightly increase the boiler pressure, then this is going to be your new cycle. Okay, so this is going to be a new cycle. So if this is 2, let us say this is going to be 2 dash and this is going to be 3 dash and this is going to be 4 dash. Okay, so by increasing the boiler pressure, this is the scenario now. Okay, now if you can see that in this case the temperature, the superheated temperature attained by point 3 is lower than the superheated temperature lower than the superheated temperature that has been attained by process 2. Okay, process 2 means increasing the boiling pressure. Okay, now as this temperature is going to be different, that means what? The temperature difference of 3 to 4 and 3 days to 4 days is going to be different. Okay, now if you want to find out the work done by turbine, for the previous one, okay, the blue cycle, okay, whatever the blue cycle is, it is going to be H3 minus H4. Okay, H3 minus H4. And work done by turbine, okay, work done by turbine for the second process is going to be what? It is going to be H3 dash minus H4. Okay, H3 dash minus H4. So obviously as its temperature is going to be higher, then obviously H3 dash is going to be higher than H3. Okay, that means enthalpy at point 3 is going to be lower than enthalpy at point 3 dash. Okay, so that means what? Your work done in the second process is definitely going to increase. Okay, your work done in the second process, okay, that means work done by turbine in second process is going to increase. Similarly, if you look at the work done by compressor, okay, or work done by pump, you can say work done by pump, then it is also going to increase. Okay, it is also going to increase. But since it is in lower temperature, okay, and the compression doesn't take place, okay, and the compression is not there, okay, that means 1 to 2 is what? 1 to 2 is just the increase of pressure, but the compression is not there. Similarly, 1 to 2 dash is also compression. 1 to 2 dash is going to be the compression for the second cycle after increasing the boiling pressure. Okay, so now what will happen? This is going to increase, but if you look at it, it is going to increase slightly. Okay, slightly such that we consider it as constant only. Okay, because the increase in the compression work, okay, the increase in the pump work or the compression work is so little that we take work done by pump as constant only. Okay, so now what you are going to see? You are going to see that work done by turbine minus work done by pump is equals to W net. Okay, and this is going to increase and this is going to be constant. Since this is going to increase and this is going to be constant, so that means what? W net is going to increase. W net is going to increase. Now again, if you see, H3 is at 0.4 dash. H3 dash is at 0.4 dash. Okay, it is isentropic to 0.4 dash. Okay, and 0.3 is what? 0.3 is at 4. At 0.4. That means isentropic. 0.3 is isentropic to 0.4 and 0.3 dash is isentropic to 0.4 dash. Okay, that means what? Entropy of 0.3 is going to be higher, okay, than the entropy at 0.3 dash. Okay, and this is the difference. Okay, so entropy at 0.3 is going to be higher than entropy at 0.3 dash by this much amount. So entropy is higher means what? In this case, heat addition was more. Okay, from 2 to 3, heat addition is more than 2 dash to 3 dash. Okay, 2 to 3 heat addition is more than 2 dash to 3 dash. That means what? Your heat input, whatever your heat input it was, after increasing the boiler pressure, your heat input is now decreasing. Okay, now if you look at the efficiency, okay, if you look at the efficiency now, what it is going to be? W net divided by Q in is going to be your efficiency. Okay, if this is your efficiency, then what it is going to be? Your W net is going to increase and your Q in is going to decrease. Q in is going to decrease. So W net is increasing, heat input is also decrease. Heat input is decreasing. That means what? This is definitely going to increase. Okay, efficiency is definitely going to increase. So by increasing the boiler pressure, we can improve the performance of the Rankine cycle. Here we can get more efficiency. And another reason for it being having the highest efficiency by increasing the pressure, due to the increase of this pressure, what is going to be there? The mean temperature of heat addition. The mean temperature of heat addition for process 2 to 3 is going to be lesser than mean temperature of heat addition for process 2 to 3 dash. Okay, the mean temperature for the second process would be somewhat here. Okay, and mean temperature for heat addition would be somewhere here. Okay, so that means what? For the second process, after increasing the pressure, we are increasing the mean temperature of heat addition, and due to the increase of the mean temperature of heat addition, your efficiency is going to increase. Now by increasing the boiling pressure, that is already method 1. Okay, so by increasing the boiling pressure, we have seen the advantage that the efficiency always increases, but one disadvantage is also there, that when it was at lower pressure, okay, it was comparatively lower pressure, we are increasing the pressure now, okay, 2 to 3, but before that it was at pressure at this pressure, okay, it was at this pressure, that means at 2 to 3, not from 2 dash to 3 dash. Okay, at this pressure it used to the boiler or the turbine exit, okay, the turbine exit or the turbine outlet, whatever the substance came out of the turbine was here at 0.4, okay, was at 0.4, but while you are increasing the boiling pressure, that means 2 dash to 3 dash, the outlet of the turbine used to come here at 0.4 dash. That means what? The steam quality previously was better. Now the steam quality has come down, okay, because it is also at 0.4 there is also the mixture of liquid plus vapor. At 0.4 dash also it is mixture of liquid plus vapor, but it is having a higher dryness fraction. It is having a higher dryness fraction. So that means what? The steam quality at 0.4 is now 0.4 was better, but now as we are increasing the boiling pressure, the dryness fraction would be lesser than the previous case. So the steam quality now, after increasing the boiling pressure, whatever the steam quality we are attaining after it has come out of the turbine is definitely going to be lower. Okay, now the second process is going to be decreasing the condenser pressure. Previously what we had done, we had increased the boiler pressure. Now this is our condenser, we need to decrease the condenser pressure. Okay, now this is the condenser, this is at this pressure. Okay, now we have to decrease it. Decrease it means what? We need to go slightly down from there. Okay, so this is going to be our boiler pressure, condenser pressure now. Okay, and this will come up to this point and this point. Okay, so after that everything is going to be same. We are not increasing the boiler pressure. Okay, so the isentropic line which comes out through the turbine is going to be same. Okay, only the 0.4 would be slightly higher. That means the previous point before decreasing the condenser pressure, the outlet of the turbine is going to be slightly higher temperature, and now it is going to be in slightly lower temperature, keeping the entropy same. Okay, so this is our going to be the final pressure. Okay, so at this pressure we are going to find out, or the pressure of the condenser has been brought down to this pressure. Okay, now from this diagram, if you look at here, then you are going to see the work done in previous case was H3 minus H4. Okay, work done in previous case was H3 minus H4, whereas after decreasing the condenser pressure, what is going to be the work done by turbine? It is nothing but H3 minus H4 dash. Okay, now H4 is higher than H4 dash. Okay, H4 is lower than H4. H4 dash is lower than H4. Okay, so that means what? This, if we consider this as the first case, if you consider this as the second case, that means what? Second one is obviously increasing, because as this part is decreasing and this part is already constant, because at this point only for both the cases enthalpy previous was H3. Okay, and this thing is decreasing, that means this thing is definitely going to increase than this one. From the first case, the second case is going to increase. Okay, so from this what conclusion can we bring? We can say that work done by turbine increases while we decrease the condenser pressure. Similarly for the previous case also we have seen that 1 to 2 was work done by pump. 1 to 2 was work done by pump, and 1 dash to 2 dash is work done by pump in previous case. So work done by pump also increases, but the increase is so slight, so negligible, that we consider work done by pump as constant. Okay, we consider work done by pump as constant. Okay, so that means what? From this case, till now we have found out that the work done by turbine increases and work done by pump remains constant. Okay, constant means the increase is so negligible that we consider it as constant. Okay, now heat increase. Okay, the increase in heat input. So previously we had to heat it from 2 to 3. Now we had to take it from 2 dash to 3. 2 dash is at a slightly lower temperature, 2 is at slightly higher temperature. So obviously for 2 to 3, for 2 to 3, for 2 to 3, the Q in was, heat input for 2 to 3 is lower than Q in for 2 dash to 3. Okay, that means what? Heat input for process 2 to 3 is lower than heat input for process 2 dash to 3. Okay, so we are seeing that heat input is also going to, heat input is going to increase. Okay, heat input is going to increase now. Okay, now you need to find the efficiency. Okay, efficiency. Now what is efficiency? Efficiency is nothing but W net divided by whatever the Q in is coming. So again, work done by turbine is increasing and work done by pump is constant. Work done by turbine is increasing, work done by pump is constant. That means what? The net work is going to increase. Okay, because this thing is constant. Work done by pump is constant and turbine is increasing, so net would be constant. And this thing, the heat input is also going to increase. Heat input is also going to increase. But compared to the W net, okay, compared to the work done by turbine, okay, compared to the work done by turbine, this increase is going to be smaller. Okay, this increase is going to be, because the temperature difference from 2 dash to 2 is definitely going to be higher, lower than temperature difference from 4 dash to 4. Okay, the temperature difference here from 4 dash to 4 is definitely going to be higher than temperature difference from 2 dash to 2. So the heat input, okay, so the heat input is going to be, the increase in heat input is going to be lower compared to the work done by turbine. Okay, that means increase in the work done by turbine is going to be greater than the increase in the heat input. Okay, for increase. Okay, that means in the increment process, work done by turbine increment is going to be higher than work done by heat input increment. So from this you can say that work done by the net work is going to increase more than the increase of Q in. So definitely the efficiency is going to increase here. Okay, definitely the efficiency is going to increase here. So what is happening? We are improving the performance of the Rankine cycle by decreasing the condenser pressure. Okay, and another thing is that previously the point 4, it was closer to the saturated vapor line. Okay, it was closer to the saturated vapor line. Now while coming to point 4 at lower pressure, it has a gap, okay, it has a noticeable gap between the saturated vapor line and point 4. That means what? Whatever the dryness fraction in point 4 dash is, okay, that means dryness fraction at point 4 dash is going to be obviously lower than dryness fraction at point 4. Okay, so that means why what again the quality of steam that is coming out of the turbine is going to decrease. Okay, so this is one disadvantage of decreasing the condenser pressure. We are improving the efficiency, but the steam quality that has been coming out from the turbine is going to be lower. The next process is superheating. Okay, so superheating means what? After reaching the superheated position, we are going to heat it more. Okay, we are going to again superheat this steam. Okay, so that means what? From in the general Rankine cycle, what we do, from 1 to 2 we compress it, or we pump it, or we increase the pressure of the water. Then from 2 to 3 we heat it. Okay, so after reaching the saturated liquid line, we heat it again. Okay, we heat it again so that the temperature of the steam again increases. Now our aim is to superheat that again. Okay, so that means what? If we superheat it at constant pressure, previously it was at 0.3, so now it is going to reach at 3 dash. We are increasing the superheated temperature is going to increase again. Okay, so after reaching here, it is isentropically going to come, and this is going to be your final cycle after you done with the superheating. So let us say that this is at 0.4 dash. Okay, so that means what? That means what? After by superheating, what we are doing? We are increasing the turbine work. Previously the work done by turbine. Okay, for work done by turbine for the first case was what? It was the difference between H3 and H4. Okay, H3 and H4. Now for the second case, okay, work done by turbine for the second case, what it is going to be? It is nothing but H3 dash minus H4 dash. Okay, now similarly you can see H3 minus H4 is H is what? H is nothing but Cp into T. Okay, Cp into T. Cp is constant, that means what? H is always dependent on, or it is proportional to temperature. If temperature is going to be higher, then the enthalpy is also going to be higher. So here you can see the temperature difference between 3 and 4 is going to be lower than the temperature difference between H3 dash and 3 dash and 4 dash. Okay, that means what? The temperature difference between 3 and 4, the point 3 and 4 is lower than temperature difference in point 3 dash and 4 dash. Okay, so this is going to be there. So from this we can say that work done by the turbine is going to increase. Okay, work done by the turbine is going to increase. Now here even the work done by pump is not even increasing slightly, it is constant here. Okay, previously it was also 1 to 2, now it is also at 1 to 2. So work done by pump is constant. Okay, but we are trying to increase the temperature, superheated temperature. So that is the reason heat input is also going to be higher. Heat input is also going to be higher. Okay, but heat input is also going to be higher, but efficiency is going to increase. Okay, again like the previous case, since turbine is work done by turbine is increasing, work done by pump is going to be constant, so W net is obviously going to increase, heat input is also going to be increased, but the concept is like the previous one. The increase in the net work is going to be lesser than the increase in higher than the increase in heat input. Okay, that means that whatever the increase in heat input is there is going to be lower than whatever the increase in W net, okay, or the network. So that is the reason efficiency is going to increase here. But now here you can see after coming out from the turbine, the last point, okay, the point 4 dash is going closer to the saturated line at same pressure. Okay, maintaining the pressure same, the point 4 dash is now closer to the saturated vapor line. Now that means what? The quality of the steam that has been coming out from the turbine is definitely going to increase. Okay, the quality is good. The quality of the steam coming out of the turbine is now good because it is closer to the saturated vapor line. Okay. The next method is reheating in Rankine cycle. Okay, now in this process, or to make this process work, we need two turbines. Okay, one at high pressure and one at low pressure. Okay, two turbines are going to be there. Okay, so in reheating, the cycle goes like this. Previously, remaining work is going to be same. Okay, so 1 to 2 it is compressing, 2 to 3 it is going to add the heat. Okay, it is going to add the heat. Now what will happen, this is going to be the first thing that we will use. It is going to be the high pressure turbine. High pressure turbine, from the high pressure turbine we are going to expand it up to this pressure. Okay, if you remember, this is the constant pressure line. Okay, this is the constant pressure line. So this is one pressure, so we are compressing it to this pressure again. Okay, we are compressing it to this pressure. Okay, so this is going to be our next pressure. That means we are expanding it to a lower pressure. Then after we are again adding the heat. Okay, we are again adding the heat. Okay, so after heat addition, the temperature again goes to the same temperature. Suppose this point is 3 dash. Okay, now as we know that the heat addition process in the Rankine cycle is going to take place in constant pressure process. That's why, keeping the pressure constant, we are going to the same temperature as that of 3, because we know that the maximum temperature is always mentioned. Okay, the maximum temperature is always going to be constant for design purpose. Okay, so keeping the pressure constant, we are again heating this to that same temperature as that of 0.3. Then after that we are going to expand it. Okay, after that we are going to expand it. Okay, so that means what we are expanding it in turbine in two different turbines. Okay, 3 to 4 is going to be what? 3 to 4 is going to be our high pressure turbine, or expansion in high pressure turbine, and 3 dash to 4 dash is going to be expansion in our low pressure turbine. Okay, so this thing is actually done to get the advantage of the high pressure turbine. Okay, if you use the high pressure turbine then most of the energy that has been coming out, okay, or the substance that is coming out contains the enthalpy. Okay, contains the more enthalpy. So we are using that enthalpy again by heating it to a temperature at lower pressure. Okay, so now in this case, if you want to see your work done, okay, or work done by turbine now, okay, work done by turbine now is what? H3 dash minus H4. Okay, this is the work that has been taken out from the high pressure turbine, and in addition there has been another work that has been taken out from the low pressure turbine, that is H3 dash minus H4 dash. Sorry, this is H3 to H4. Low pressure turbine is H3 to high pressure turbine is H3 to H4. Okay, H3 minus H4 is the work taken out from high pressure turbine. H3 dash to H4 dash is the amount of work taken out from the low pressure turbine. Okay, that means this is the low pressure. Okay, now that means what? Work done by turbine obviously increases if we do reheating. Okay, if we do reheating, work done by turbine increases. Now heat input is once from 2 to 3, and again it is from 4 to 3 dash. Okay, heat adding is also taking place in two different passages. Okay, 2 to 3 at constant pressure, again 4 to 3 dash, again at constant pressure we are adding the heat. Okay, so here Q in also increases, but work done by the pump is always going to be constant here. Okay, 1 to 2, the heat the work done by the work done to a pump. Okay, work done to a pump is always going to be constant here. Now coming to the efficiency, it is hard to tell whether the efficiency is going to increase or not. Okay, it is hard to tell whether the efficiency is going to increase or not, because in this thing we do not know where the mean temperature of heat addition would be. Okay, we do not know where the mean temperature of heat addition would be. Now for the given conditions, if the conditions are given, then we will know. In the given condition, if we find out that the mean temperature of heat addition is greater than the previous one, normal Rankine cycle. Okay, if this is the normal Rankine cycle, okay, in this case, if the mean temperature of heat addition is lower than the mean temperature of heat addition than this reheated process, then efficiency will obviously increase. Okay, but if the mean temperature of heat addition is higher in this case and lower in this case, then efficiency is going to decrease. Okay, so it is hard to tell whether the efficiency is going to be increasing or decreasing without the proper data being given. Okay, so this is going to be another process to improve the performance in Rankine cycle. Okay, now we are going to see regeneration in Rankine cycle. Okay, regeneration is also a process of improving the performance of Rankine cycle. Okay, so this is the layout of Rankine cycle. Okay, now the diagram may look a bit awkward, or you may say that it looks something difficult, but if you understand, this is going to be very easy topic. Okay, now in the previous parts of the Rankine cycle, we have always seen that there was a pump which used to take the water and it used to boil. Okay, after that there used to be a turbine, it used to compress it, expand it, and after that it used to pass through a condenser. Okay, now the common things are going to be here also. Boiler is also there, condenser is also there, high pressure turbine and low pressure turbine are the two turbines here. Okay, high pressure and low pressure are the two turbines here. Okay, now what is the difference from of it from the other parts? Okay, now let us suppose 1 kg of steam has been coming out from the boiler after taking the heat. Okay, or after the heating process has been completed, 1 kg of steam is coming out. Okay, now we are going to have a high pressure turbine. Okay, after high pressure turbine, what happens? After high pressure turbine, an amount of the steam that has been expanded out of the turbine, an amount y, suppose y kg of steam has been taken out. Okay, and the remaining, at first it was 1 kg, so when y kg has come out, now the remaining thing is 1 minus y kg. 1 minus 1 y kg, what is this 1 minus 1 y kg? This is nothing but another part of the expanded steam that has been taken out from the high pressure turbine. And that steam, that 1 minus y kg of steam is now passed through the low pressure turbine. And again it is expanded. Okay, and again it is expanded. After that, whatever the expanded part, okay, the substance that has been come out of the low pressure turbine after the expansion has now been passed through a condenser. Okay, and what is the work of a condenser? It condenses it from steam to the liquid. So whatever steam or water vapor mixture was there, it has been completely transferred to the or it has been completely coming out of the condenser. Okay, so it is now being pumped out by pump 1. Okay, so that 1 minus, so the amount of steam that is coming out from here is 1 minus y kg only. Okay, 1 minus y kg is passing out, then 1 minus y kg of steam is fed into the feed water heater. This FWH is nothing but feed water heater. Here no external heat is there. Okay, no external heat supply is there. What is happening here? Whatever the steam that has been taken out, y kg of steam that has been taken out after the expansion from heat pressure turbine, leaving this one. Okay, so this amount of heat was containing some amount of enthalpy because this was not completely expanded. This was not completely expanded. So whatever the amount that has been taken out from the high pressure turbine is now collected here. Okay, and whatever the steam that has been expanded completely by a low pressure turbine, this is now going to get cooled down after the expansion, and after passing through the condenser it is going to get cooled down again. So whatever the cooled down water that has been coming, okay, it is again being added to the feed water heater, and the water that has been coming out from the low high pressure turbine without expansion, without full expansion, okay, this amount of steam is going to heat the steam that is, or heat the liquid that has been coming out from the condenser. Okay, so what is happening, and 1 kg of 1 kg mass of steam is coming. Okay, so after partially expanding, some of the steam is being used to heat up the steam that has been fully expanded by this low pressure turbine. Okay, so low pressure turbine outlets are heated by the high pressure turbine outlet, part of the high pressure turbine outlet, and the remaining thing is again going to pass out through the low pressure turbine, condenser and pump 1. So after pulling it from pump 1, okay, it is depositing it into the feed water heater, where it is being heated by the steam, partially expanded steam that has been coming out from the high pressure turbine. Then there is another pump, okay, pump 2. So from pump 2 it is again going to the boiler. Okay, so this is the main thing. Okay, so nothing is different here, only some of the heat is taken or some of the steam is taken out to heat the remaining part. Okay, so let us come to the TS diagram. Okay, previously in Rankine cycle, whatever the axis were drawn, all the terms or all the plots were T versus S diagram. Okay, in some places I may not have written T or S. Okay, so all the in Rankine cycle, all the graphs that we have drawn would be T versus S curve. Okay, now let us represent this regeneration cycle in TS diagram. Okay, what happens after coming out from boiler? After coming out from boiler means what? After heat addition process. So heat addition process completes here. Okay, we all know. Okay, so before that you must remember that 1 dash, 2 dash, 3 dash and 4 dash is going to be our normal Rankine cycle. But regeneration cycle consists of 1, 2, 3, 4, 5, 6 and 7. 1, 2, 3, 4, 5, 6, 7 consists of the regenerative Rankine cycle in TS diagram. Okay, so coming to the point, whatever the 1 kg of mass that has been coming out from the boiler. Okay, so after expanding, it is going to divide its path in two different ways. One is going to pass through the low pressure turbine and other is directly going to the feed water heater. Okay, so what is happening here? What is happening? After heat addition process, it is going to expand. Okay, so up to here, up to this point, it is going to be expanded by high pressure turbine. Okay, now after that, it is going in two different ways. One is coming in this way. Okay, one is coming in this way means 6 to 7 is one expansion process. 6 to 7 is again expansion process. So this is going to be low pressure turbine. Okay, that means what? 6 to 7 is a low pressure turbine. 6 to 7 is a low pressure turbine. Okay, so 6 to 7 is a low pressure turbine. Okay, and the remaining part. Okay, so in low pressure turbine, what is the amount of steam that is coming? It is nothing but 1 minus y kg. 1 minus y kg steam is coming through the low pressure turbine, and the y kg part, okay, or y kg, the amount of steam that is coming out or it is parting its path away from the high pressure turbine is going there. Okay, it is not going there actually, it is helping the steam that is coming out from here. Okay, after passing through the low pressure turbine, it is going to pass through. Okay, it is going to pass through the condenser again. 1 minus y kg is going to pass through the condenser again. After that it is going to get saturated or it is going to get converted to saturated liquid. Okay, so after that what happens? A pump is there. Okay, pump 1. Now pump 1 acts here. 1 dash to 2 is the work of a pump. Okay, or 1 to 2 is the work of a pump. Okay, so after pumping, what happens? The heat addition. 2 to 3 is the heat addition process. 2 to 3 is the heat addition process, and this heat addition process, this particular heat addition process from 2 to 3, okay, is nothing but due to this feed water heater. Feed water heater means whatever the y steam is coming out with some amount of heat is going to heat the 1 minus y kg of heat. So this 1 minus y kg of heat is going to heat up this 1 minus y kg of steam from point 2 to point 3. Okay, point 2 to point 3 is the heat addition process, is going to be heated by 1 minus y kg of steam is going to be heated by y kg of steam. Okay, so after that there is 3 to 4. 3 to 4 is what? 3 to 4 is nothing but another pump is going to work. Okay, so here it would be 0.4. 3 to 4 there would be another pump P2. Okay, it is increasing the pressure from point 3 to point P. Okay, so it is increasing the pressure again. After that this boiler is going to, after that this boiler 4 to 5 is going to be the heat addition process by this boiler. Okay, so the remaining things are going to be same, but only thing is here part of the steam is going to come out which is going to heat the remaining part of the steam. Okay, so it is a kind of preheating. Okay, so preheating of the steam is going to take place in this regeneration cycle. Okay, and here the entropy is going to increase, not entropy, sorry, efficiency is going to increase. Okay, efficiency is going to increase because by doing this process we are increasing the mean temperature of heat addition. Okay, by increasing the mean temperature of heat addition we are going to increase the efficiency. So this regeneration in Rankine cycle is also used to improve the performance of the Rankine cycle. Okay, now we are going to see the work done, okay, heat input and what is the work done by pound for the regeneration cycle. Okay, now the first thing that comes to our mind after hearing the positive work, okay, or the work done by the turbine is nothing but in this regeneration cycle work is going to be done in two different parts. Okay, so one is work done by the high pressure turbine and one is work done by the low pressure turbine. Okay, now for the high pressure turbine, what is going to be the work done by turbine? Work done by turbine is now nothing but H5 minus H6. Okay, that is the work done by the high pressure turbine. Okay, now the amount of mass, okay, which is doing the work in high pressure turbine is 1. Okay, so we are not multiplying 1 here, and along with this there will be the work done by the turbine or the low pressure turbine. Okay, now what is the work done by the low pressure turbine? Now this is the expansion process in high pressure turbine. 5 to 6 is the expansion process in high pressure turbine. Now after that what happens, there is two different paths. Okay, one is going with y amount of steam or y kg of steam, and another path is there 1 minus y kg of steam. Now that 1 minus y kg of steam is going to pass through the low pressure turbine. Okay, so this is the low pressure turbine and the mass that is associated with this turbine is nothing but 1 minus y. Okay, and what is the enthalpy difference now in the low pressure turbine? It is nothing but H6 minus H7. Okay, this is the amount of heat, work that has been taken out from the low pressure turbine. Now let us consider for one moment the original Rankine cycle. Original Rankine cycle here is what? 1 dash, 2 dash, 3 dash and 4 dash is our original Rankine cycle. Okay, now according to that Rankine cycle, okay, according to that Rankine cycle, what would have been the work done by turbine? It would have been H3 dash minus H4 dash. This would have been the original Rankine cycle work done by turbine. Okay, or original Rankine cycle positive work. Okay, but now in the original cycle what has been done, H3 to 3 dash to 4 dash, it is coming out with mass 1 kg. Okay, it is coming out with mass 1 kg, but due to this regeneration cycle or due to the application of this regeneration, what is happening? The same distance, okay, 3 dash to 4 dash, the same distance is now being covered with two different steps, 5 to 6 and 6 to 7. Okay, the enthalpy amount would have been, if the temperature was same, the enthalpy amount would have been same. Okay, here also same case. Okay, but the work done by turbine is going to now decrease. Why? Because though it is the step we are covering in 2 steps, okay, or this is the total distance we are covering in 2 steps. Okay, 3 dash to 4 dash is distance, covering it in 2 steps, 5 to 6 and 6 to 7. Okay, so up to 5 to 6 the amount of mass is same for both the turbines, for the original Rankine cycle also and the regeneration Rankine cycle also. From 5 to 6 it is associated with 1 kg of steam, but from 6 to 7 here y amount of steam is less now. Okay, there is y amount of steam less now, so the work done by the low pressure turbine in second step is going to be now smaller. Okay, so that is the reason why work done by turbine is going to decrease in case of regeneration in Rankine cycle. Okay, now coming to the heat addition process. In heat addition process what happens? There is also 2 steps of heat addition. 2 to 3 is one step and 4 to 5 is another step. Okay, now 2 to 3 the heat addition process is not given by us. Okay, or whatever the heat we need to give for making the point 2 to 3, okay, it is the heat that is not given by us. That heat has been recovered from the steam that has been coming out from the high pressure turbine itself. Okay, whatever the partially expanded steam that has been coming out of the turbine is from that steam, the 2 to 3 heat is recovered. Okay, or the heat addition process from 2 to 3 is recovered. Now the amount of heat that we have given is from 4 to 5. Okay, so this is the total amount of heat that has been given by us, so that would be considered as the total heat input. So total heat input would be what? H5 minus H4. Enthalpy difference between point 4 and 5 is going to be our heat heat addition process. Okay, now work done by pump. Okay, now the pump work is what is the work of a pump? It is nothing but increasing the pressure. Okay, now initially it was at pressure 1. Okay, now with the pump we require to reach the temperature of 0.4. Okay, now this is a constant pressure line. Okay, and this is also a constant pressure line. Okay, so reaching from 1 dash to 2 dash, reaching from 1 dash to 2 dash, that is in case of original Rankine cycle, 1 dash to 2 dash is same as that of 1 to 4 in regeneration Rankine cycle. Okay, 1 dash to 2 dash is same as that of 1 to 4 in regeneration Rankine cycle. Okay, only thing is that we are going from pressure 1 to pressure 4 in two different steps. 1 dash to 2 dash and 1 to 4 is same pressure difference. Okay, but we are going in two different steps. Okay, so since we are going in two different steps, since we are going in two different steps but the pressure difference is same, work done by pump is going to be constant or very negligible. Okay, very negligible change would be there. Okay, so work done by pump in case of original Rankine cycle would have been same as that of the work done by pump, or sorry, not work done by, work given to the pump. Okay, in case of regeneration cycle. Okay, so there would have been very negligible change of work given to a pump. Okay, so this is going to be constant. So if you come to W net now, okay, what is going to be the W net? W net is nothing but work done by turbine minus work given to a pump. Okay, positive work minus negative work. So this is obviously going to decrease because turbine work is decreasing. Turbine work is decreasing and this is constant. So W net is going to be constant. Q in is what? Q in is heat addition process. Okay, so in case of normal Rankine cycle, okay, your heat addition would have been from 2 dash to 3 dash. Okay, for normal Rankine cycle your heat addition would have been from 2 dash to 3 dash, but in regeneration Rankine cycle the amount of heat you want to give is from 4 to 5 only. Okay, from 4 to 5. Okay, so Q in is also decreasing. Q in is also decreasing. So now if you consider the efficiency, here W net is decreasing, okay, divided by Q in, that is also decreasing, but efficiency will increase here. Why? Because the decrease in the heat addition process is much more than the decrease in the W net. Okay, so this thing will be, the decrease will be more, so this amount will be lesser and lesser. So the decrease is more means what? This amount will be lesser. Since this amount will be lesser, this and the decrease of this amount is not going to matter, so efficiency is going to increase. Okay, and another explanation for that would be the efficiency increases just because the mean temperature of heat addition is now going to increase. Okay, mean temperature of heat addition is now going to increase. That is the reason the efficiency is now going to increase. Okay, now we are going to see the energy balance in feed water heater. Okay, in feed water heater what happens? Y kg of steam comes from the high pressure turbine. Okay, Y kg of steam comes from high pressure turbine and 1 minus Y kg of steam comes from low pressure turbine. Okay, after coming from low pressure turbine it passes through condenser and after that from 1 to 2 it passes through pump. Okay, after that it reaches to feed water heater. Okay, so this would be at what? This would be at 0.2. Okay, after 0.2 it reaches feed water heater, gets heated and reaches to 0.3. Okay, after heating the point is this. Okay, and where does Y come from? Y come from 0.6. Okay, from 0.6 it comes to direct feed water heater. Okay, so this would be 0.6. This is this is going to be 0.2 and this is going to be 0.3. Okay, now for energy balance is what? What is going to be the energy at inlet is going to be equal to the energy at outlet. Okay, so with what energy this is going in? Y with the enthalpy of 6. Okay, that means Y with enthalpy of 6. Mass into enthalpy is going to be the inlet energy from high pressure turbine. From low pressure turbine, the energy is going to be 1 minus y kg into what is the amount of enthalpy? Enthalpy is nothing but H2. Okay, so H2 would be the enthalpy. So y into H6 plus 1 minus y into Ht is the energy at inlet. Okay, and with what enthalpy it is going to come out of the system, okay, or come out of the feed water heater? This is 1 kg. Okay, so it would be at 0.3. Okay, so it would be H3 into 1. Okay, so from the energy balance of the feed water heater, we are going to see that H3 is going to be equal to y into H6 plus 1 minus y into H2. Okay, so this is our energy balance of feed water heater. From this relation, we are going to find different values which we are asked to find. Okay, so with this we have completed our Rankine cycle. Okay, so after that we are going to start refrigeration.